to meet up here together with our kind speaker, Ondřej Hulík, who came to us from University in Belgium, and he brought a very interesting topic for us. It's somehow try of rethinking the symmetries, supersymmetries, I guess.
Just normal
symmetries, okay. And he will show us some paths from BF theories to T-duality.
Yeah.
So thanks, Ondra, for coming, and we are very curious.
Thank you. Okay, should I close the door? Or,
yeah, sure.
Okay. Okay. Thank you for giving me the opportunity to speak here. And I come from physics background, so apologize beforehand for maybe giving you some not complete mathematically rigorous definitions of things, but hopefully I'll at least be able to give you some very concrete examples of what I want to talk about today. And so the main topic here, so everything will revolve around internal symmetries, which is sort of a hot topic of these days. And before I jump into this T-duality related things, and I just want to tell you a bit about what are symmetries in quantum field theory and how we generalize them. And I will try to tell you a bit in what it means in general, but I'll also try to illustrate that on examples, because that's always the best way to learn something, for me anyway. And the examples hopefully should be pretty familiar to people. One of them will be just regular old two-dimensional boson, which is probably familiar to everyone, right? And the second one will be Maxwell theory. And last thing, which is where we're gonna really step into this newer stuff, will be BF theory, where things will become more interesting. But yeah, okay, let's start. So first, so just like old symmetries, I guess. Old symmetries. Is this readable? Is it big enough? Yeah. Okay. All right. Okay. So basically, when we talk about also disclaimer, when I talk about symmetries, I really mean symmetries in quantum field theory, which means global symmetries. Local symmetries are not symmetries, right? There are some ambiguities in description, and so we're talking global symmetries here. And in physics, when we talk about global symmetries, the regular ones, there's always a matter theorem behind, which tells us that there's a current, right? So for every global there's current, conserved current. Conserved off shell, which means that there's some continuity equation, which looks like this. J is some one form that will be the current associated with the symmetry, and Decker is just a dual of the Viron operator, right? So it's like a divergence equation. What this allows us to do several things. First, it tells you that you can define something like a charge, right? You can integrate over a time slice, and it defines a charge which is constant in time. Is that clear from the equation? Okay. So this is infinitesimal information about that. Second, more important thing is that, and that will be crucial for us, is that it allows you to write some topological operator. So what I mean by that, if I massage this equation a little bit, it means that star R J is 0, right? And if I remove this star, it's still 0, right? And now I see that whatever is in here is something closed, right? So now if I construct an operator out of this n-1 form. So this was one form, right? This is now the -1 form. I can integrate it over some surface. So say I will have some three-dimensional space, and here I'll have some surface operator, and of codimension 1. Sorry, D, right? Capital D, the dimension of space. So the star will make it into D-1. Now I can integrate it over codimension 1 surface and construct this operator U, which will be exponentiated surface integral of this star J over sigma. So that's something natural I can come up with. I can also put some number here, T, and then distinguish all these. There's a whole class of these operators, which will be numbered by this prefactor P, and they will be of this kind. So now this operator is topological. What it means is that it doesn't really matter over which surface I integrate this. So if I do a tiny little deformation to this surface, right, I move this one a little bit, I can use this equation, right, and use the Gauss law in that little bit of space here. And it tells me that as long as there's no insertions, meaning the right-hand side is really 0, I can move it and the operator remains the same. It does the same thing. Does the same thing in the sense that if I put it in the correlation function in my QFT, I will get the same result if I wiggle this surface a little bit. But this right-hand side, it can change, right? So this is only true in classical field theory. There could be sources on the right-hand side which will alter this equation locally, right? So what can happen is that instead of 0 here, I could in principle have some delta function insertions with some charge E. Okay. The thing about this is instead of wrapping some empty space, having some insertion of some xi here of some associated charge E. Okay. And now if you do the same calculation, if you start wiggling and shrinking this surface, you can go as far as infinitesimally, reaching this point, nothing will change. But once you flip over, right, once you go over this point with the surface on your deformation, you will see this right-hand side, and it will enter into your Gauss law, right? And that will result in not equal operator, but it will be equilateral phase. And this phase will be E to the I P. Okay. So E will be from this prefactor here, P will be from this, right? So that's why I put this extra P here. Okay, so now the way to interpret this is that these topological operators, they sort of they are applied on all the operators in your field theory, and they read off the charge of a specific operator. I will for today, I will only talk about abelian symmetries. There's also a way to deal with non-abelian ones, but it's more complicated. So this is something you should now think of as local operators being charged under some U1 symmetry or maybe some discrete symmetry, and these topological operators being something what reads up the charge, right? And so, I mean, in general, I guess they could also change the operator, but here I'm assuming that the objects in my field theory are all diagonal under that symmetry. So it's really just reading of this charge PD, right? And this P would be like a something what parameterizes say U1 symmetry, right? So this P will be responsible for a point on the U1 of the group which is being represented. And this E is a charge. Okay, so that's that's like the basic way we would think about the symmetries from conserved currents. Now, there's a natural generalization if you have this geometric picture in your mind now, and that is that you could maybe before I go to the generalization, I'll just give you an example to internalize this. So in 2D boson, we have such symmetries. So what would be your action? It will be so what origin would be this thing? Okay. I'm assuming that it's compact boson, so the target space is some U1. And now there's actually two regular symmetries, two one forms which are associated to these symmetries. One of them is d phi. That's one form, right? So this is some Jm. I'll explain why Jm. D phi. Okay, so there's these two currents. Notice that if I now apply this d dagger, this one is closed if the equations of motions are invoked, whereas this one is closed always, right? So actually switch that. So this one, right, dagger J E to 0 if we use ELM, whereas this one Jm is 0 always, right? There's no restriction on going on shell. So these ones are special in a way. These kind of symmetries are called topological because they don't need these equations of motions. So the one which is what is the symmetry associated to this current? If I sort of gave you that example upside down, I started here. So this one, if you quantize your 2D boson and look at what this guy generates, this one, you'll see that it's just a shift of phi. And indeed, like this action has obvious shift symmetry, right? Phi goes to phi plus alpha. These derivatives kill it. So there's no alteration to the Lagrangian. This one is a little more complicated. This one actually measures monopole charge or vorticity of some operators in your theory. I'll try to explain that, giving you the charged objects in the theory. So JE, that one is simple, as I said, it generates the shifts of phi. So JE generates phi equals to phi plus alpha, and the sort of operators which are diagonal under this theory, they are these vertex operators people might know from string theory. P phi, usual vertex operators in 2D boson. So you see that if I shift this guy by alpha, the phase pops out of this operator, right? But also I can do it in a more geometric way. I can define this thing. I can define now a line operator, which will be some Q line of this JE star. So this is a line operator. It's topological because of that. And it reads of the charge, it reads of this P of these vertex operators. But also, you know that in, or maybe you don't, but in 2D boson, there's other types of vertex operators if the target space is compact, because you have winding, right? And these windings, they allow for more general vertex operators, which not only have this P momentum, but they also have the winding, which is coupled to this dual boson, right? And it's this charge which is read by this magnetic charge. So that's slightly less visible in this frame, but under T-duality, if people are familiar, these two degrees of freedom, they get exchanged, right? This is the normal frame, and this would be the T-dual, like the dual field, and they get swept under T-duality. And fairly enough, these will get also switched, because in T-duality, you'll get this relation which connects target pi. So you see that what was J electric, it is mapped to J tilde magnetic and vice versa. So now you see that in this phi tilde frame, in the T-duality frame, sorry, in the dual frame, under T-duality, it's the phi tilde which gets just naturally shifted, and therefore you will be reading of this W charge, whereas the P guy will be a little bit complicated. Okay, so that's something nice, where you can already see the some nice symmetries in the 2D boson. But remember this structure of electric and magnetic, because it also appears in Maxwell theory. There's also some sort of topological charge and normal charge, but there will be these one-form symmetries, which I'll talk about now. Okay, is this clear? So this was just regular symmetries, just put in more geometric fashion, right? And I showed you how they both really high. How they can act as some line operators. Okay.
There is a wish from online audience to write it a little bit bigger.
Okay.
Because
right. Okay. Yeah. Okay. So there is a generalization now, which is the higher form generalization, and what it really means what you probably expect. Like I will not start with one form there, but I'll start with some n form, right? So if I instead of having one form, I'll replace with J K form. I can now which is co-closed, right? Again, the dagger J K 0, so it's co-closed. Then I can define again topological operator, just because of the same Gauss law reasoning, but on a higher codimension surface, right? So maybe to be complete, because it usually gets ugly with d minus k minus 1, whatever numbers. Let's think of being in 4D, because that will be my next example. If I'm in 4D and say I will find some 2 form, and unfortunately now there's no deriving it from Lagrangian, but it's just that if I happen to find a 2 form which is co-closed, which there will be in examples, so maybe 2 form, I can now construct this e to the I q surface now star 2 form, which is again 2 forms, right? So I can integrate both 2 surface inside 4D. But now, what would be the charged objects under this? If it was just if it was just a point in 4D, and I had a surface, right? Surface in 4D, which is hard to draw. I could remove it from within that surface, right? I can use my extra dimension to remove this point. So clearly, any point I have, I cannot really think of as being charged under this higher form symmetry, right? But there could be higher normal operators in my field theory, which is not something exotic. Maxwell theory supports such operators. And indeed, if I have a line operator, for instance, that has an appropriate codimension with this surface operator, which admits for non-trivial linking, and those objects can be charged under these 2 form symmetries, one form symmetries. Right. So again, like this is a general idea. You just replace 1 forms with k forms, same logic. You can have insertions which screw up the Gauss law, and you can therefore have some charged operators of higher dimension. All right, so is that clear? Kind of. Okay, so an example is good to give you some something more concrete. So 4D, which will be very much reminiscent of this thing. So in 4D, we have Maxwell theory, which looks like this. Okay, and now you could now define two forms actually. There's a two-form F, and there's a two-form F star, right? So both of them are two forms, and you see that a similar thing happens here. Those two forms, they this one. Both of them are closed. One of them requires the equations of motion to be satisfied, right? Because if you recall, the equation of motion is to be here, b and then 0. And the other one does not require that at all, right? That one is just this one, right? This one is just topological because this is just a star, right? And if I apply star, B star, there, that one will just kill it right off the bat. Okay, so one of them is again trivially closed, the other one is not, and that allows me to define again two operators, two line operators. Sorry, two surface operators. One made out of these, and one made out of these. And without going into too much details, you can read in the literature that the line operators, which are charged under one of them, under the electric guy, are the Wilson lines you can construct in this theory. And the other ones, they were more complicated there, and they are more complicated here as well. Those are the top lines, right? Which again, you know that you cannot write in the regular frame. You need to go to S dual frame now instead of T dual frame, and there they become Wilson lines of the dual field, and thing sort of mimics that. So due to lack of time, I won't go into details of this example, but it very much mimics what I outlined in the 2D boson case. So Wilson lines are the nice ones. They were the usual fields like that. Top lines, which are charged and magnetic, they are the more complicated operators, and they work nicely in the dual frame. All right. Okay. So that's for the higher form symmetries. And now I'll move to the main example where I'll try to give more details, which is the BF theory and Chern-Simons, and I'll try to explain more of what's going on and what are the symmetrics in there. Okay. Are there any questions at this point, or? So now I'll give you some basics about the BF theory, what are the observables and what are the symmetries in the theory, and then I'll move to the discussion of boundary conditions and how it relates to the 2D boson, and then I'll try to, if time permits, give you some information about this T-duality from the BF point of view. So BF theory it's really just if people know Chern-Simons theory, it's almost the same thing. It's just a theory made out of two forms of complementary degree in a specific sense. I'll explain that in a minute. Minus one. Okay. So contrary to Chern-Simons, this can be defined in any dimension, and you always need just forms which wedge with the D in appropriate volume form which you can integrate. However, I'll restrict myself to 3D. Although in 3D you can also have several of them, right? You can have like a 5 times D2 form maybe, or you can have one form. So I'll mostly focus on these, but it's also good to have in mind that there's this one existing in 3D. So 3D, yeah, these. Okay, so what are the? I will maybe first give you a bit of geometric picture of what's happening in here for these ones, and then I'll move to line guys. And so what's happening here? There's two. There's first one thing you need to decide, and that is as to where your fields are taking values, and that will have a drastic implication on what are the observables in the theory. So I said that I will only do abelian stuff here. So the only two options are that these guys take values either in U1 or R. Okay. And what is the so I will make this table. So first, if I'm in here, so U1 valued phi and B, there's also a mixed case where one of them would be U1 and the other one R, or vice versa, but let's not get into all the details. So if I'm in this window, I have both of them being valued in U1. B2, you can use words like chirp connections for it. It's not really two-form, but yeah, probably better than me what that objective is. But if this is really valued in U1, you know that the phi is now a compact boson, and so it's defined up to shifts of the of 2 pi plus 2 pi and for that reason, phi itself is not a good observable, but e to the phi is also not a good observable. But if I choose the appropriate p here, which will be quantized now, right, because of these shifts, it is good observable, because if I shift and this p will be in the dual lattice, right, here I can shift with some finite steps. So if this p will be in the 1 over r z, these will be good observables. So you see that a priori, you can maybe think of that you have all these vertex operators available, but this fact that it lives in U1, it restricts it down to some integral spectrum. Right. Same thing is true for B, which requires some more explanation, but just to say, due to the fact that it's a chirp connection valued in one, and that there's large case transformations, these integrals over free space will be quantized. Some r times 2 pi z. And that leads to the same restriction. So a priori, you would say, okay, so this is not defined in and of itself, right? It's up to gauge transformation. So I would just make these be over surface. But now, instead of allowing for any q here, it gets cut down to some integral lattice, again, for the similar reason as here, okay? So these are two types of observables you can construct here in the BF theory with U1 valued field. In this slot, you have no restriction like that, okay? No, there's no large gauge transformations. There's no ambiguity between writing phi and phi plus 2 pi n. So now you can just construct these vertex operators which have p valued in the whole real line, and same for these guys. So it's almost identical, except for in one case it's just integral lattice, and here it's r times r fields. Okay, cool. There will be caveats with that, but I'll get to that in a moment. In this case, it's the exact same. You just have two one forms for the similar reason of quantization of the field. Because of the U1 valuedness, you'll end up with two types of lines. M and then A, whereas here you'll end up with alpha, maybe theta E, and alpha A. Okay, so these are all your observables you can have, and BF theory is funny because it's those things have sort of these observables. They play a role of both topological operators, so they act with some symmetry proof action, but also they play a role of observable. So that's something strange about this theory. It's because it's topological. Is it clear? This last statement I made, all of these operators are topological. It's because if you would vary these two actions, you'd see that the equations of motions are just that d of something is 0, right? And then you can play the same game with deformations of objects and so on. All right, okay, but they are somehow, they have non-trivial linkings. So I will get to that now. I will try to explain that maybe in the 0, 0,2 cases. Okay. So there's non-trivial linking among these operators, and what is crucial for that? So imagine now that you have this B line and A line. So B line equals the I P P.
So what's the difference with Chern segments?
Sorry?
What's the difference with Chern segments?
Chern segments, it's almost the same as this underscribed example.
Yes,
but
that's what I realized. It's already by mosquito. So.
Yes, but the B is equal to A, right?
Yeah, right.
And the difference is that then you don't have really two types of operators. You have just one set, and they're self-linking. Yeah. So yeah, it's almost the same, but not quite. Yeah, it's yeah. You can also talk about these general abelian Chern-Simons theories, which will be defined like this, where this is some symmetric two form, and maybe it's just one-dimensional matrix, then it's Chern-Simons. In my case, it would be some of diagonal 1, 1, but you can have all sorts of interesting examples. And there's this paper of Saulina and Kapustin, and they studied these in great detail for various reasons. But okay, so now let's consider this situation. Let's think that I'm calculating a correlator of these two Wilson lines. This one maybe continues to infinity, or maybe closes up somewhere. They cannot be opened. I maybe didn't stress that. Right? If they were open, the gauge invariance would make them transform at the ends. So there would not be gauge invariant observable. So they have to be closed lines. Right. But okay, so they're both topological because of the equations of motion, but they cannot cross, right? Once they cross, they generate linking. And the linking can be calculated explicitly. It's a free theory, so I can calculate the propagator. I can actually calculate semi-classically. I'll take the propagator and integrate over this and this line, and I'll see that I get some Gauss linking number. But what is crucial in that calculation is that if you do it properly, there will be this prefactor n. So if I normalize my EF theory properly, like this factor will enter in my linking. So the linking, when I undo the linking, it will differ by this factor 2 pi I over n dq. Okay. So that would be the phase I obtain upon pulling two lines and unlink them. So what does this tell me? Is something interesting. Is that so say the R is 1 here. So now I see that P and Q. I'm looking at the window number 1. I see that those generic lines, they have linking, but if I take one of those P's or Q's to be multiple of n, it doesn't link with anything, right? And we call these lines transparent. And so the logic is that among all these z by z, there's z times z worth of lines in here. It's only really z sub n times z sub n which are effectively doing something, right? Because then there's this whole plethora of lines which are just transparent, and you might as well just discard them from your theory because they're just not doing anything, right? So this link, is this clear? This statement?
I don't think so. I'm not really aware of. So is it somehow obvious why this prefactor comes in?
So this comes out of calculation. That I mean, I would not probably do it in real time here, but it's not hard calculation. It's just that you need to calculate the propagator of that free field theory, and you need to integrate it basically over this line and that line, and you'll identify it with the linking. So you'll see that if you undo it, that will result in this factor of the previous linking. But once you, so this you should take for granted. But if you take this for granted, is it clear that there's this reduction from z times z to cn times cn? That's more important for now, I think. Right? It's just because, you know, if one of these, say p, if p is n times some other number x rather than an integer, this is always 1, right? So if one of them is like that, I can always unlink them, and it's as if they weren't there, right? They just do not contribute into calculations by any non-trivial phases. Yeah. I'm not saying that, I mean, the other, like now there could be still some lines which are transparent to some other lines, but I'm saying that this specific subset is transparent to everything, right? So that therefore it's useful to sort of discard them. So now quantum mechanically, meaning this, I get further restriction of this spectrum z times z to zn times cn. That was the statement I wanted to make, right? So I'll really just add n here and n here. Okay. Whereas here, there's no such transparent nothing, right? Because it's all valued in R. I will always, you give me one p here, whatever multiple of integer of any kind, I'll always find something what links with it, right? So I don't have really any distinction of, you know, I don't get this cutting down of the spectrum, whereas here I do. So in particular, what's interesting here is that if n was 1, right? The theory would be trivial, even though it looks a bit non-trivial. If the level is 1, it's trivial theory. That's the consequence of the statement. All right. Okay. Okay. So that's the. Oh, that's not much time left. Okay, so that's the BF theory. Now we know the spectrum and we know how the things are linking. And what's interesting is that you could now interpret one of these lines as the generators of the symmetry on the operators, which are the other types of lines, or vice versa. It's sort of symmetric and dual in this sense.
There is a question in the chat. What if I wanted to if I one can shrink the loop on the right picture to a point?
Yeah, I mean, I can. Sorry, maybe I didn't explain that well. But what I meant is that suppose that I'm calculating it's a QFT, right? So the only thing I'm always doing is calculating some correlator. I want to calculate this kind of correlator of two linking circles. The way I would calculate it is that, well, either I do the hard work and calculate the propagator, but now that I know these general properties, I know that I can unlink them first. I get this space, Q over N, Ti, times linking unlinked circles. And those will just give me some normalization factor. So I know that I can now take all, I know that all my observables are some lines of some kind. They can link non-trivially, but I can always undo all the linkings. I will always produce some non-trivial phase factors times some unlinked correlator. So this was sort of a recipe to calculate any correlator within this theory with non-trivial operators. That's what I was trying to do.
Fritzo wrote that he had in mind that two pictures as an action. If we can see these two pictures as an action of the loop operator on the line operator.
Yes, that's sorry. I think I said that in different words, but yeah, you can always think of this one set of objects as being the generators of one form of symmetry in this particular sense on these ones, or vice versa, right? Which ones are which? That's just a matter of interpretation. So you can think of ones as they're all topological. So I can think of one set as the matter lines for movement and the other ones as the symmetry lines or vice versa. But here it doesn't really matter. It's just words. It's just the same calculation going on.
Yeah. Okay. Apparently answered.
Okay, perfect. Thank you. Okay, so right. So now one extra ingredient, which is interesting, and that's when we have a boundary, and that's really where I'm heading with these examples. And so let's introduce boundary to this picture. So now I'll have BF theory here, BF theory, and some boundary. So nothing on the left from this line, and so as usual on field theory, if I have a boundary, I need to prescribe some boundary conditions so that my theory is well defined in the variational process. And so there could be more interesting boundary conditions. I'll mention one later, but the most basic ones, which we can have, are on either B or A type of lines. Okay, so let's again specialize to this one form case. One can analyze everything, but let's take this and let's take Dirichlet for B. Dirichlet or B. Okay. So if I take Dirichlet for B, one thing happens, and that is that now suddenly, so before in the bulk, which is still true, I can have these closed loops, right? But now, thanks to this boundary condition of B being 0 at the boundary, I can have B lines ending at the boundary. That's a new thing, new feature I can have. A lines can only still be in the bulk, while B lines can end at the boundary. And it will be good gauge invariant operator. So B line, it's like that. And A lines are just still just some closed loops. Right. So now now there's a nice interpretation of these things, and that is that I can think of these B lines ending in the boundary as generating some local operators at the boundary, right? Because they end at the boundary. There I can think of there being some operator phi stuck into that point where the B line ends. Okay. The A line, on the other hand, well, that can be anywhere. It can also sit at the boundary. That's fine, and it will be exactly some symmetry generating operator. Now that I've sort of chosen this duality frame, if you will, I'm thinking of B lines as being the honest measure lines, which are generating some local insertions at the boundary, and the A lines are something which generates symmetry. Right? So the way they do it is that they enclose my B line, and I can undo it, and I can generate the face, and I can either do it in the bulk or I can do it at the boundary. It doesn't matter. It's fine. One little footnote here. What if classically nothing would prevent me from putting Dirichlet boundary conditions on both B or A, right? I mean, if I vary this, it tells me that B delta A needs to be 0 at the boundary. If B is 0, great. If A is 0, also even greater, right? But this is actually a problem. The thing is that the rule of thumb is that I can only let the lines end at the boundary which are mutually transparent in the bulk. So that's a rule, and I'll try to give you argument why. So right, all the B lines link trivially with all the B lines. It's only the A lines and B lines which have non-trivial phase. If I allowed A lines also end at the boundary, the thing is that I would get something inconsistent, because on one hand, I could take this A line and I could undo it here and produce a phase, but I can also go to the boundary. Now the A field is 0 at the boundary, and I can undo this line, and it will just become, maybe I'll make the picture more 2D-like. So I would have this A line, I would push it to the boundary, and it will trivialize there. So now I can open it, and I can take this line outside of it, and then I can pull it back to the bulk, and I would produce no phase at all. So on one hand, in one calculation, I will get a phase here, but in the other way of pushing it to the boundary first and opening it and unlinking and then pulling it to the bulk, I get no phase, so it's inconsistent. So the rule is that I can only let the lines which are mutually transparent and at the boundary, and the other ones will be the symmetry operators. So the theory which I obtained here is not something very physical, but the interesting physical stuff will come from this R sector. But nevertheless, I can think here that it's actually physical, but I will not go into details here. I have some theory which has Zn worth of local operators. And there's a Zn symmetry, Zn discrete sum, zero form symmetry. These local insertions of the boundary. So that's the picture here.
That's the boundary theory.
This is a boundary theory, okay. Yeah. And it comes from this Z1 one form symmetry in the bulk. Yeah.
Sorry, can I ask you one thing?
Yes.
So, the example before, the inconsistency was if you require Dirichlet for both.
Yes, yes.
Right?
Yeah.
But that doesn't make maybe the whole theory inconsistent. I mean, can I write a theory and impose those boundary conditions? I would say maybe it's breaking the symmetry.
It's
I just want to understand if it's an inconsistency of the theory or just breaking some symmetry.
I would say it's inconsistency of theory because now because all these things are calculations of some correlators.
Mhm.
And now you see that because the correlators are now in the full space with the boundary. And now this one way to calculate this, pulling it out, or the other way, pushing it to the boundary and unlinking, would yield different results, right? So it's it would give you two results to one type of correlator, which is unwanted. Yeah.
Well,
Yeah. Okay. All right. So, but yeah, is that more or less okay? Are you?
yeah, I would say it breaks the symmetry because the operators are not topological anymore. You can't shift them around because that's inconsistent to pull stuff around.
But I can still push them around because of my equations of motion. You know, they are topological. Nothing's changed about it.
Yeah, I absolutely understand your point, so it's fine.
Okay.
Maybe it's just a matter of timing.
Okay. Yeah, we can maybe
Just
discuss after.
yeah, no, thanks.
Yeah. All right, but now I'll show you slightly more interesting setup with some different boundary conditions in the R case. So, and that will finally get us at the right moment, I guess, back to the 2D boson. And okay, so what about the R case? So again, R with the two line operators type of things. And there's B lines and A lines. If you recall in the table, now the charges are unrestricted. So there's R times R worth of A lines and A lines and B lines, right? Both of them cannot, for the same reason, if you agree, to enter the boundary. But now, I mean, I can again do these fully polarized, if you will, Dirichlet boundary conditions, which will result in some theory which will have all the B lines ending. So there would be R worth of local excitations at the boundary, and A lines would constitute symmetry operators. So that would be one option, or turning it around and A lines ending and B lines being the symmetry operators. So that would result in theory with R worth of local operators and some non-compact R group acting on those local operators. But I can do something more interesting. And something more interesting is this thing. I can have my, so I told you that the rule of thumb is that the only thing which can enter the boundary at the same time must be a set of lines which are mutually transparent. And I can choose some combination of B and A lines, which are mutually transparent. So if you remember, the linking looks like this. Now the level doesn't matter. I can subsume it into redefinition of these alpha and betas. So linking is this. And you see that if I choose alpha to be in some lattice, R times D, and this one in the dual of this, 1 over R, D, they're transparent, right? So out of all the R times R lines, I choose this Z times Z subset, and I'll let all these A and B lines, which are integrally charged, enter the boundary. So I can do that, and they're mutually transparent. And now, okay, so now I can do that. I can have A lines ending, and but with the restricted charges, A lines, which restricted. and B lines also. And okay, so this we're doing this one, we're doing that one now. So they're mutually transparent, but there's still lines in the bulk which cannot end at the boundary, but they will facilitate the symmetry action, and they will be the component. They will be the R which are not in R R times Z or 1 over R times Z, which is U1 and U1 dual in a way, right? So there's still these remaining A lines and B lines, B lines, with here R mod sorry, this at R and this is my little r or normal capital R. So these are still something what acts at the boundary, okay? And so now you see that you have this interesting setup, that you have two sets of boundary degrees of freedom, which are so the boundary I'll have R RZ times 1 R RZ real Fs, and there's a U1 times U1 dual symmetry. But that's very reminiscent of this 2D boson setup. There you have your vertex operators, which were of this 1 type phi and 1 type phi tilde. They were both integrally charged because of the compactness of the boson. And then there were these two shift symmetries, one nice one, if you remember, one little bit ugly one, right? And I claim that this model is sort of 3D uplift of the original 2D boson. Okay. So yeah, so this boundary theory now for this BF with the R valued one forms in this BF sense is so-called 3D TFT for this symmetry. Okay. So that's nice. But what's more nice is that you can now analyze everything you're doing to your 2D boson in this 3D uplifted sense. And that's maybe the last thing I'll just briefly comment on, because I'm probably running out of time, or I have
5 minutes for these.
Okay. And that is that we can construct some other operators. So I should, at this point, I should say everything what came before was sort of old stuff, well, not that old, but from various papers. Now, this new stuff is work in progress with amazing team of people from ULB in Brussels. Okay. Right. So there's these other type of operators you can now construct. They're called condensation effects. And basically what they are is that you can take your original lines and you can compose them into something more complicated. So I'll just give you the formula here so that I'm not just talking. Okay. All right. Okay. So you can construct this C sigma. And it will be some something made out of these alpha A of A cycle and plus cycle. And here there will be an integral over r valued h1 sigma. There. So that looks weird, but what it really is that now you should think of having this boundary and having this surface operator, sigma. And well, this has a homology generated by these lines which are perpendicular to the boundary and parallel to the boundary, right? Some A lines and B lines maybe. And now if you integrate this whole thing or all the possible lines, you get some surface operator. And what's interesting is that it kind of it facilitates the duality in the sense that if you take this line, so yeah, just to give you intuition, rest like the details you can see in the paper if you're interested, or I can tell you more. But basically these A lines and B lines, they were kind of like the phi tilde in the compact boson. And now this line, this surface now acts on these lines. And the same thing basically happens. Like you can wiggle it around in your inside your tube here, but once you cross, you generate some non-trivial winding with the B cycle, produce some phase, and this thing will do its thing, and it will basically exchange A line and B line. So A line will go to B line, and B line will go to A line. And yeah.
Absolutely simple. True.
Yeah.
Why do you integrate with the co-homology process and not homology?
Sorry, you're right. Yeah. All right. Yeah, you integrate over these cycles with the R valued coefficients. Yeah. So thank you. And so this provides you with this operation on the lines, which sends A lines to B lines and B lines to A lines. And if you look at what it does to the boundary, it's exactly the T duality. So that's kind of a nice thing that you can uplift it this 3D sense. And the story doesn't really stop there. I need to stop here, but the story doesn't stop there. There basically everything you can imagine doing to your 2D boson, we have now translation to this 3D topological field theory description, meaning that discrete symmetry gauging, what people do in 2D CFT in condensed matter contexts, there exists some condensation defect for that. There's defect for befolding your theory, or doing T-duality, which links different radii, and like all the other operations can be sort of encapsulated in these condensation defect operators. But yeah, for the lack of time, I think I'll stop here and yeah.
Thank you very much.
Thank you.
Very insightful talk, and it might inspire us for many questions. So I open question panel for this time. So maybe I would have a question concerning the first part where you discussed the difference and the relationship between Wilson lines and Toft line.
Mm-hmm.
Could you explain me what the second?
Yeah.
Things?
Right. So do you have some understanding of this 2D boson setup that you can exchange phi and phi?
Kind of.
Okay. So I'm just asking because in Maxwell it's exactly the same. It's just that you replace phi with A and phi tilde with some A dual, and the same thing has both three. So basically, right, you can have this dA star dA, and in 4D, I should have stressed that you know that this two form, if I apply star, it's two form again.
Mm-hmm.
Now I can ask myself, okay, find the potential for the star DOA, right? And how this potential is till now. The thing is that I can rewrite my my original action in terms of this new degree of freedom, this dual degree of freedom. And what happens is, just like in T-duality, there's some 1 over G squared free factor. This one gets flipped, right? So in T-duality, there's 1 over R, and it will get flipped, right, to large radius instead. Here you go also from like small coupling to large coupling and vice versa. That's the basic S-duality. And the thing is that this is S-duality at the level of Lagrangian, at the level of basic fields, but it extends. So basically, what were the Wilson lines? Wilson lines are just these simple operators. Whereas top lines are not so easy to define in this frame. They can be defined through path integral by specifying some blow up of your gauge fields. On the other hand, in the dual frame, if I go to dual frame, I can just write down the Wilson lines for these dual fields, and they are all nice and easy. But what were the original Wilson lines named up to top lines in the other frame? So that's kind of what's happening.
Yeah, exactly.
Yeah, that's. So yeah, it's always this trade-off. Like you have some nice operators and some ugly operators, and that really permeates a lot of models. Like there's this Hegel in 3D duality between gauge field in 3D and compact boson, and now the lines are met to some vortex operators and vice versa. So it's kind of omnipresent feature of many gauge theories. And 2D boson, which is, well, I guess, with this bizarre version of next level.
Cool.
Yeah.
Thank you. So, any other question?
So follow up on this, I don't understand. So what is the phi tilde learning? For example, in the bulk, what corresponds to phi tilde in the bulk when you uplift it in the
In here,
yeah,
it was the
so kind of phi was the end of the line which could end at the boundary.
yeah, okay. So do you in 2D boson, if do you know physics of 2D? Okay, so you know that if it's the compact case, right, you'll have momenta which are 1 over R, where R is the size of the target circle. So momenta will be 1 over R times n, and the windings will be R times n. And in those mixed Dirichlet boundary conditions I defined, you see the similar feature. So to really link it to here, it's a little bit more work, but at least you see that the charge lead is identical, right? You see that I had to choose mutually transparent lines, and one of them were R times Z, and the other ones had to be 1 over R times Z. And these will correspond to winding and momentum excitations at the boundary.
What I didn't understand is that it's that simple, like one of the two fields correspond to phi and the other of the two fields correspond to phi tilde.
Yes.
That was mine.
Or well, the ending line endpoint.
Right, yeah, it's like a dimensional reduction on the boundary. Okay, yeah, thanks.
Okay, any other question? Look on the chat whether it's there. Yeah, it doesn't seem to be the case. So for this moment, I would like to thank you again for responses. Postpone other questions to informal panel, which also.